Hello everyone. For this tutoring video, I would like to discuss the lever, as well as the physical concepts behind it, such as center of mass, torque, or moment of inertia. The first thing to notice is that a lever is simply an object that rotates around a fixed point, formerly called a fulcrum. We will next notice that rotational motion is different than the linear motion we are used to, although they can be correlated to each other by using a radius of a circle. For example, an object that rotates in a smaller circle will be able to rotate faster than an object that rotates in a bigger circle, i.e. a circle with a wider radius, because it has less distance to cover. Just like traditional linear acceleration is denoted with a lowercase a, angular acceleration is denoted with the Greek letter alpha. And we can notice that linear acceleration equals angular acceleration times the radius it is rotating around. Manipulating this formula, we get the angular acceleration is equal to linear acceleration divided by the radius. This makes sense from our everyday experience, such as with pushing a door, as when you push with the same strength or force, but at a greater distance from the hinges, i.e. the fulcrum, you get a greater acceleration. Just like how we can relate angular acceleration to linear acceleration, we can relate a rotational version of force called torque to the regular force. Torque is denoted with the Greek letter tau and looks like this, a T with a tail, almost like a backwards J. Or sometimes the stem is at the bottom, and the left-hand side is curved instead. And we can state that the torque will be equal to the radius of the force times the magnitude of the force. Although these are not the only two factors affecting torque. As for example, if you push directly in the direction of the hinge, you will experience no torque regardless of how hard you push. But if you push perpendicular to the direction of the hinge instead, you will get maximum force. This can be expressed mathematically as the sine of the angle between the radius and the force. And the sine function will be maximum when the force is exactly perpendicular to the radius, i.e. like this. And will be minimum, i.e. 0, if the force is directly in opposition to the radius. As the sine of 0 is 0, and anything times 0 is also 0. From this formula, you may already be able to notice that for a greater radius, you would need a smaller force to do the same exact work. And this is exactly how levers work. For example, if we place the pivot point in the middle instead of the end, so that the example becomes something like a seesaw, and the forces will have the same mass, then the one with the longer distance will cause the lever to rotate. Because the forces are equal in this example, so the only factor that could be changed is the radius, aka the distance. If instead the distance is kept the same, but the masses are different, then the one with the greater mass will cause it to tip over in that particular direction. As we remember that the force a mass exerts is equal to its mass times its acceleration due to gravity. And the only factor that we can change is the mass. Acceleration due to gravity is constant near the Earth's surface. The next subject I like to touch on is the center of gravity of a system. As you may have already noticed, almost all real-world mechanical objects are much more sophisticated than simple geometric shapes. But we can simplify the mechanics of it regardless of the geometry by assuming all mass is concentrated around what is known as the center of mass. The center of mass is a fancy way of saying the distribution of the masses along all the axes of the object. So in this example, we can assume that the center of mass is right in the exact geometric center of the lever, due to the fact that it is a rod of uniform mass. But if we have a more sophisticated object, like say a human body, we take notice that the mass is greater in the top half than the bottom half of the body. So the center of mass is more upward than the geometric center would suggest. If you can figure out the center of mass of an object, you can also therefore describe all motion relative to the center of mass. So for example, a force applied on the center of mass or very close to it would cause linear motion, whereas forces applied at a radius from the center of mass would cause rotational motion. If the forces that cause rotation in reference to center of mass are in equal amounts at both distances, for example, in the seesaw example, if both masses are equal and at the same distance, then the object will experience static equilibrium, meaning that there will be no torque or no force causing it to accelerate. However, if there is an uneven concentration of forces instead, either because of their distance or their magnitude, then they will give the object a torque. and the direction of whichever force is causing the most disturbance. Now that I've shown you that center of gravity can actually be different from the geometric center of an object, I can move on to discussing moment of inertia, which is the rotational equivalent of mass with linear acceleration. Consider, for example, holding up a very long and thick rod that has an obvious mass, so it feels heavy in your hands. As we already know, it is mass distributed all along it and not simply at a few points. This means that if you attempt to rotate it at one of its endpoints, you are actually rotating more mass when you rotate it in either direction. So because of the sheer amount of mass that you're trying to turn at once, it will be very resistive to it. However, if you were to rotate it around the exact center, you would find it is actually easier to rotate, because now you are rotating half the mass here if you do it clockwise, and half the mass here if you're doing counterclockwise. As such, we denote the formula for the moment of inertia as capital I equals the total concentration of the mass, m, times the radius squared, where radius is the distance from the axis of rotation. It is important to notice the square in this, meaning that for the same exact mass of an object, it will be harder to rotate at a longer distance than at a shorter distance, by a very dramatic factor. For an object that has basically an equal concentration of mass all around from its radius, for example a bike tire, we can tell that because the smaller tire has a smaller radius, it will rotate with more ease than a bike tire with greater radius. However, it's more complicated than that, as many objects, such as rings, have their masses concentrated at a great distance from the center, as opposed to having an even distribution of mass like many wheels. Remembering that radius impacts the rotational inertia more greatly than the mass, we can see that a ring and a wheel of the same exact radius will have very different rotational inertias, and the ring will rotate more slowly or be harder to rotate than the wheel. With all of that out of the way, I can move on to teaching wheel and axles next week, as they also use rotational motion just like levers.